Now for multi-class classification problems, the activation of choice for the last layer is the softmax activation for last layer. So imagine a neural network that takes a lot of inputs in, let's say, layer 1, and in layer 2 it also has a bunch of neurons, and finally it has 3 neurons in the last layer where the outputs of each of these neurons, let's say, indicate the probability. Let's say the first one is the probability of cat, second one is the probability of dog, and the last one is the probability of, let's say, horse. So we have our input here, and the input flows through the network, and essentially at the end these 3 neurons predict whether the output is a cat, dog, or a horse. And say we have 3 images. This is my image number 1. This looks like a picture of a cat, and here's a picture of a horse, and here's a picture of a dog. And say for the first picture, the neural network output looks like this. The output from the cat neuron is a 5, the output from the dog neuron is a 4, and the output from the horse neuron is a 2, right? So this is not very helpful because looking at these numbers, I cannot really tell what the model is predicting. So it would be easier if I was given something like a probability that this picture belongs to that of a cat or a horse or a dog. So then that's where the softmax function comes into play. So if I want to convert these predictions, these outputs from 3 neurons, into probabilities, then I can apply the softmax function. So the way softmax works is we simply exponentiate the inputs for each class, and then in the denominator we sum these exponents for each class, and then for each class we obtain the corresponding probabilities. For example, in this case my output will be e to the power 5 divided by e to the power 5 plus e to the power 4 plus e to the power 2. So this gives me the probability that it is a cat. Similarly, if I wanted the probability for dog, then I would do, so since the output for the dog is 4, I would do e to the power 4 divided by e to the power 5 plus e to the power 4 plus e to the power 2. So this gives me the probability that the picture is that of a dog. So the beauty of this output is that now my entire, this all output, each of total sum of all of these is equal to 1. This way, this output now serves like probability. In a way, now I can say, okay, so given this picture that we have, the probability that the picture is that of a cat is that it is a cat is 0.71, and the probability that it is a dog is 0.26, and the probability that it's a horse is 0.04. Now in this expression, the softmax output here, k represents the number of classes. So this is the number of classes. In this case, our number of classes is 3 because we have a cat, dog, and horse. And here e is the standard e value, and z is the actual output from the neuron. Zj is the output at node z, and k is the number of classes. One common activation is sigmoid, particularly if used for binary classification, and sometimes even used as activations in the intermediate layers of a neural network. So the sigmoid function is basically 1 divided by 1 plus exponential of the negative of your input. The beauty of sigmoid function is no matter what input it receives, so if this is our input, right? So if this is our input and this is the output of sigmoid function, then no matter what your input is, the output is always between 0 and 1. That's the really good beauty of sigmoid function. It squeezes your inputs such that your output ranges between 0 and 1. So the range of this function is 0 to 1, and the domain is minus infinite to plus infinite. So of course, to get reasonable values, you have to have reasonable input. It is also known as the S-shaped curve. And it's also very easy to understand and apply. That's why sigmoid is very popular. Now, there are some problems with the sigmoid function, and one of the biggest problems is the problem of vanishing gradient. Now, what this vanishing gradient problem means is, say you have a first layer L1 and second layer L2 and third layer L3 and let's say fourth layer L4. So the output of, let's say, this neuron when passed through sigmoid, right, will go out and maybe add as input to the other layers. And once again, this neuron gives you an output between 0 and 1, and it also goes out as output to the subsequent layers and so on. So now, since sigmoid has the tendency to either squeeze everything towards 0 or make everything a 1, because of the many zeros that it could potentially produce, the numbers that come out from this layer eventually start becoming smaller and smaller. So if my input here is 0.1 and the input in this next layer is 0.005, then subsequently this becomes so small that the underflow, the floating point of representation, cannot handle the small value outputs of the neural network. So this is a common problem of sigmoid. Also, its output isn't zero-centered. So since its output is 0.5 centered, so the middle value is 0.5, this also sometimes creates problems for neural networks to learn. Particularly, this makes the gradient updates go too far in different directions. So if the output was zero-centered instead, it would be much easier for the gradient updates. This basically makes the optimization process harder. Also, sigmoid converges slow. The convergence with sigmoid is historically, as known from logistic regression, very slow. Another common activation function is hyperbolic tangent, sometimes used in place of the sigmoid function. The difference between sigmoid and hyperbolic tangent is that sigmoid ranges from 0 to 1. This is your output range of sigmoid, whereas the hyperbolic tangent function ranges from -1 to +1, effectively solving the problem of zero-centeredness, non-zero-centeredness in the sigmoid. Now, in this case, the range is -1 to +1. The output is zero-centered, which is a solution compared to the sigmoid. Optimization is easier in case of hyperbolic tangent. In practice, hyperbolic tangent is always preferred over sigmoid if we want the output not necessarily to be if we want the output to be between 0 and 1, then sigmoid is the way to go. But if the output can range from -1 to +1, then hyperbolic tangent is the choice. This still suffers from the vanishing gradient problem. Very recently, a very simple activation known as rectified linear unit, or ReLU, has become very popular. And the activation function is extremely simple. It is the maximum of the 0 and the input. And it has become very popular in the recent years. It's very simple. This is the default ReLU plot. So if the input is more than 0, then the output, so if this is my input, then the output is same as my input, just like the linear. But if the input is less than 0, then the output is always a 0. So it turns out ReLU is actually, even though it looks extremely simple, it's very, very powerful. Now, because ReLU, in a way, discards everything that's negative, and sometimes this could create problems when learning, researchers came up with variations to ReLU to address that issue of ReLU. One variation is the leaky ReLU, where instead of making everything less than 0, if your input is less than 0, instead of making it 0, you multiply it with a constant and then obtain a slightly different kind of input, not exactly linear, but you still want to ignore or sort of minimize the effect from small values, but it's not exactly 0. And another approach to change ReLU is to use randomized leaky ReLU. That is, instead of fixing the value of AI, you randomly choose AI such that this score fluctuates in a certain range. But despite these variations of leaky ReLU and randomized leaky ReLU, ReLU still remains very popular as an activation function now. A slightly more computationally expensive, but sometimes slightly more accurate, or like sort of leads to better accuracy activation function is the exponentially linear unit, also known as LU. So if you have a small data set and if you are looking for a activation function, then I think the default activation that one could choose for all the layers other than the last layer, I would suggest is LU, because it has the benefits of ReLU, the simplicity of ReLU, also has techniques to mitigate the limitations of ReLU. So in LU, if your input is more than 0, then it behaves like the standard ReLU, where the output is same as the input. But if your input is less than 0, then we use this function, slightly exponentiated version, but not exactly 0, but close to 0, the diminishing input. So the anything below 0 has some voice or something to say in the output, but not much, and in a way squashed using this activation function. The linear activation, which actually effectively means no activation at all. It means no activation because this actually does not transform the data non-linearly in any way. This is very easy for your optimizer to solve, and a linear function is just a polynomial of degree 1. And because it's just a polynomial of degree 1, it is limited in complexity to capture deeper patterns in input data. They have such a network in which all the activations are linear has very little power to learn complex functional mappings from the data. Basically, a neural network without activation function is what is a model with linear activation model. So basically, a neural network model without activation function or all linear activation is equivalent to a linear regression model. Basically, no matter how many layers you have, if all your model has is all linear activations, then your model is effectively a linear regression model. Here's how a linear function looks like. If this is your input, then the output is same as the input. Except for the last layer, it is actually never advised to only have linear activations in your neural network. So sometimes for the last layer, so if we have intermediate layers in neural network, for the last layer, you may want linear activation, but for all the layers before that, it is almost never advised to have linear activation.